So let's have a look at the stuff we're going to revise. So as normal, it's under courses, computing, 10 GCSE computer science, theory. Thanks for all the comments, Ella. I'm just picturing that at home you're just sat there with your head going, ah, I can't take it. Right, so let's have a look. So this is Unit 2 that we finished. We were doing pretty well with, but I just want to do one lesson revision because it's been a few weeks since we looked at it. Okay, so the first part was what I think is the toughest of all the stuff we have to do, which is this one here, the central processing unit stuff. So we had to know what these registers do: the program counter, current instruction register, accumulator, memory address register, memory data register. We had to be able to understand the arithmetic logic unit, the control unit, and then how cache works, and that ultimately the CPU has to talk to memory. I've actually revisited that a few times. We might come back and do that again, but I want to look at what other stuff is there first. There's then the factors that affect the speed of a CPU. So the three we need to know about were cache size, clock speed, and number of cores. You need to be able to say what those things are, how they make a difference to the speed of the computer, and what their limitations are. So clock speed can't keep getting faster because we can't control the temperature anymore. Number of cores makes a difference on multitasking. It makes very little difference on linear operations where we have to wait for the previous instruction to finish before we can do the next one anyway. And cache size is useful in certain programs. It's very useful in a lot of programs, but there's a trade-off. If you give more cache, then the cache slows down. If you have less cache, the cache is fast, but there's less of it. So a balance there to get the best speed out of the computer can be quite difficult. Then we looked at what primary storage is. Primary storage being the memory that CPUs fetch and execute directly from. And these are the different types of... I'm going to zoom this in because obviously you're probably not getting the full resolution screen as easily. Too big. Yeah, probably not getting the full resolution screen as easily in YouTube, so do it this way. There we are. So those were the types of cache memory we need to be aware of. RAM, random access memory, that's the main primary storage used in PCs. It's that one that's lightning fast but volatile. However, CPUs will also fetch and execute instructions from ROM. That's read-only memory. It's memory that doesn't... let me just fix that annoying green screen artifact up in the top right. There we go. It's memory that you can't change once it's been written. So it's useful for the booting up of the computer. Once the computer is first switched on, it goes to ROM to find the instructions of how to get going. Because we can't delete ROM, it means the computer will always be able to start up, which means we always have a way to fix it if something goes wrong. Flash memory is things like memory sticks, SD cards. It's hardware, it's memory on a chip that is non-volatile. It can be erased, not as easily, but it stays there permanently. Cache memory we know all about. We've done lesson after lesson on cache memory. That's the very, very fast memory inside the CPU that stores frequently used instructions. And then virtual memory we did towards the end of it, which was where we put instructions when we run out of real memory. It's a section of secondary storage of the hard disk where we can copy banks of real memory to in order to stop the computer from crashing, but it causes massive slowdowns. But generally, it's better that the computer slows down than stops running altogether. So that's what it's for. We then had... Oops. We then had to talk about secondary storage devices. So optical, magnetic, solid state. What we haven't covered is cloud storage. I didn't realize that had snuck its way onto the specification. We'll do a bit on that in a minute. But optical was things like DVDs, CDs. They're becoming obsolete, but they still exist in games consoles, and they work by having a laser reflect off a surface, and if it reflects, it's a 1. If it doesn't, it's a 0. Magnetic, those are still the most popular types of storage because they are very, very cheap for the size of them. They work by having magnetic particles that are either polarized north to south or south to north to represent 1 or 0. but they're very fragile. They are power hungry, they're noisy, they're slow. Solid state, which are the most modern things, they are fantastic. They're very fast. They are very reliable. Don't use much power. They can be made very physically small, but they're still more expensive than magnetic, so that's why they're not taking off as much as they will do. Cloud storage we'll look at in a second. Yeah, we need to be able to compare them in terms of that. And then finally, for these last two sections, which were about the extra components in a computer. So GPUs, graphics processing units, these things that have thousands of cores instead of just instead of say 6 or 8, but they only do a very small set of things. They're designed to do certain things incredibly quickly, and those certain things are usually associated with graphics in a video game. So be able to do the vector maths needed to calculate where something will go or how light will reflect off something. GPUs do that very quickly, but they can't do much else. Sound cards, same thing but for audio. They do sound processing really quickly and really well, but nothing else. And motherboards is that big circuit that everything plugs into. So when we took the computer apart at the end of last term, we were taking everything out of the motherboard, then plugging it back into the motherboard. And finally, embedded systems. Now I only mentioned this right at the end because there really is nothing more to it than just understand that what an embedded system is. An embedded system is simply a whole computer system, so the processor, the memory, and the input-output that's necessary, all on one board or even on one chip that's usually embedded into something else. So yeah, for example, I've got my drawing graphics tablet here. This will have an embedded processor in it which deals with the Bluetooth connection to the computer. It will also deal with detecting the strength that the pen is pushing on and stuff like that. So there'll be a tiny little embedded computer in here doing all that stuff. But obviously it's not going to make a motherboard with plug-in things. It's all embedded onto one chip. Okay, and that was it. That's all the stuff we need to know. So for this lesson, if people put some things in the comments, or the comments down this side, if you put some stuff in the comments, let me know of those things I've just talked about, what would it be most benefit for you for me to revisit? Now, my throat's just dried up completely. I need to bring some water in here. Let me know which ones would most benefit for you, and we'll spend this lesson revisiting the one that most people say would be helpful. So type into the comments. Those comments are really productive so far. But if we type into the comments of those things I've just talked about, what would you like to revise? And also, to respond to Kieran's email, Dylan is at school. They're sat in a classroom doing the same things you are, where I'm away in a little box stood in front of a green screen doing this. It's kind of weird. So embedded systems, I'm guessing that's Kyron. Kyron, embedded systems literally is just the stuff I've said. There is nothing more to embedded systems. You just need to know what an embedded system is. It's an entire system on one chip or one board that goes inside something else. There is nothing more to it than that. Just remember that definition and that's all of it. CPU, yeah, there's quite a lot to CPU. CPU is like a third of this entire unit. So what aspect of CPU? The speed, the factors affecting the speed of the CPU, the registers inside a CPU, the other components of it, the fetch execute cycle, that's all CPU. Which ones in particular? And yes, Heath, don't forget to smash that subscribe button. Jewel Weewoo, who is that? I can't figure out who that is from that name. So yeah, the registers inside a CPU. That's fair enough. I think that is the toughest part of this. Let's just go back. We'll basically just do that again. Look at the fetch execute cycle again. Hopefully, because it's been a few weeks since you've done it, this will just get those things back in your brain. So let's find the fetch execute cycle. Okay, well, I'll move this podium a little. This all looks really smooth on YouTube, like I've got this really sleek setup. But if you actually see in here the pile of wires on the floor and the stuff I'm trying to avoid while moving around here, it looks chaotic in here. Right, so let's have a look at fetch execute cycle and things. So Yeah, I won't do that again. Oops. Right, so first of all, there was this definition. It's fascinating. In the actual class, you guys are one of the best classes I've had for listening when I'm talking, for paying attention and only talking when you need to. Once we get a chat window, you guys are typing garbage constantly, not listening to a word I'm saying. It turns out you can't handle chat windows, but in person, you're brilliant. So let's quieten the chat down a little bit while I go through this. For most people, this will really benefit and you'll do a lot better next lesson if you listen to this one. So leave the chat alone unless I ask something just while we go through this, please. Right, so computing devices. A computing device is any device that takes an input, processes it, and produces an output. Okay, we just need to know that definition, not much more than that. I'll move on to the rest. And computing devices don't necessarily just mean PCs and laptops and things like that. It's anything that does that. So, so out of that, there's only a toaster and a webcam that would not be classed as a computing device. All the rest will take an input, will process it, will produce an output. And all computing devices do what they do because of an amazing little device called the CPU, the Central Processing Unit. The Central Processing Unit fetches and executes instructions from memory. That's just a definition we have to know. If you get a question in the exam that says, what is the role of the CPU? It's to fetch, decode, and execute instructions from memory. We've just got to remember that. But how it does that is a little more complicated. So yeah, you've already got these notes here. You don't have to make notes again. Where do I point? There, that's it. So I'll try and act like I can really see this on the screen behind me. Yeah. Right, the Central Processing Unit fetches, decodes, and executes instructions from memory. And when we say memory, we're talking about addressable memory that looks like this. So we've got a series of addresses in there, and in each address, some data can be stored. So in this particular snapshot of memory, in address 10,134, this data is stored. Thanks, lupus. I think I just thanked a disease. I'm not sure who lupus is, but when we do a register, we'll find out. 10135 doesn't have any data in it at the moment. 10136 has that data in it, and that's how memory works. It has a series of addresses, and we can put stuff in there. So, just put that a bit more useful position. There we go. All right, so I'm reading the chats, and seriously, can we try just a little bit to stay on topic? It is a Latin word. It is also a disease. So whenever we say memory, we're referring to this. Okay. So when we say a CPU has to fetch and execute instructions from memory, the instructions will be in various different memory locations, memory addresses. So this one up here, this one up here might be an instruction to do something. Then underneath it will be the next instruction. Then underneath it will be the next instruction. Underneath it will be the next one, etc. And that's where the instructions are. So the processor's job is to get this data out of the appropriate place, execute it. Then get this data out of the appropriate place and execute it. And then get this one out of the processor, out of the memory, and execute it. And how it does that, let's just jump ahead through the fancy animations, is with these. It uses these registers here. The program counter exists to keep track of which memory address it wants to store. So if we go back to this diagram we had here, if this bit at the top here is the address of the first instruction, then that value 10134 will be in the program counter because that is where the first instruction is stored. Oh, why does it stop scrolling? Oh, there we are, we're back. The current instruction register here, let's point at that there, current instruction register here is where that actual instruction that's just been fetched is put. So I'll go back up here again. So if the program counter had 10134 in it, then we get this value here out of 10134, and that goes into the current instruction register. So the current instruction register stores this, which is the instruction we want to run. Then these two underneath, the I don't know how weather people, the guys that present the weather on the TV, they make this look so effortlessly. I can't point to the right thing first time for life. Here we are. The memory address register and the memory data register Those ones are the registers that are used to actually get stuff out of RAM. The memory address register is connected directly to the address in the memory, and the memory data register is connected directly to the data in the register. So if I go back up here, when I wanted to get this value out of memory, what I did was put that value, 10134, into the memory address register. That told RAM that we want this data, so it puts this value into the memory data register. So now my CPU has access to that value, and it can put it into the current instruction register or wherever it needs to go. And the final register is the accumulator. Whoops. The accumulator nearly. Oh, come on, I can do this. I can do this. Oh, no, it started lagging behind. There we are. The accumulator. The accumulator. Where are we? Yeah. So the accumulator is used during calculations. So if we are adding multiple things together, the running total will be kept in the accumulator. So the accumulator and the new value keep going to the arithmetic logic unit. It adds them together back to the accumulator. So that's what they're for. So this fancy little animation explains the same thing. I'll go through this again. So if we were wanting to actually run a fetch execute cycle for a very simple program like this one. So this one will load 3, then add 5, then store 10. So it loads the number 3 into the accumulator, adds 5 to it, and then stores the accumulator value in memory location 10. That's all it needs to do. So first thing we do is we load that program into memory. So that will appear here. So load 3, add 5, store 10, and they're in address 0, 1, and 2. That's where that stuff gets stored. Then we start the fetch execute cycle. So first thing we do is fetch the first instruction. To know which instruction needs fetching, we look at the program counter. Ooh, I've clipped off the edge of the screen, that's not good. We look at the program counter. The program counter contains the address of which instruction is going to be used next. In this case it's 0, so that means we need to fetch load 3. So in order to get load 3, we have to put 0 into the memory address register. So 0 goes into the memory address register. Because that's in the memory address register, RAM will see, oh hang on, they're asking for address 0, I'd better give them this data here. So load 3 will appear in the memory data register. There we go. And now that's in the memory data register, but we can't leave stuff in the memory address register and memory data register because every time we access RAM, that stuff changes. We need to keep track of which instruction we're running, so that instruction moves up into the current instruction register. And that's where we are now. That's our first fetch. We have now fetched the current instruction, which is load 3, put it in the current instruction register. We're ready to execute it. And also, while we're doing that one, the program counter incremented, so we know the next instruction to fetch. Then we execute that instruction. So we know that we've got to load 3, so we load 3 into the accumulator. There it is. That's that instruction been executed. So we've now fetched and executed our first instruction. Now we need to fetch the next instruction. So we look at the program counter to see which one to get. It's 1, which is going to be add 5. So 1 goes into the memory address register, add 5 appears in the memory data register, and then we copy that over into the current instruction register, and then we'll fetch the next one. We execute it because we need to add 5 to the accumulator. So both 3 and 5 are sent to the arithmetic and logic unit. The addition is done there, and 8 is put back into the accumulator. And then the last instruction is store 10. So same process is done to put store 10 into the current instruction register. Now what that instruction is asking us to do is to store something into memory location. So the memory is switched to write mode. We don't have to worry about how that's done, it just is. That's done to write mode, and if we want to put the value of the accumulator, we want to put 8 into location 10, we have to put 10 down here into the memory address register and 8 into the memory data register. Right, guys, while I appreciate this is all very entertaining, what you're now doing is getting other YouTube videos and passing them around and saying, oh, you watch this. That's the equivalent as if I was delivering a lesson going, actually, there's a much better lesson going on over there. Why don't we all go and watch it? We put a lot of effort into this. Can we make the effort to watch this, please, and not pass around other videos to watch? Thank you. So with 2 in the memory address register, there it is, 10 in the memory address register and 8 in the memory data register, that will send that over to RAM so that 8 will appear in location 10. And there it is. So that's how fetch and execute works. Ultimately, they're not going to ask you for step-by-step of the stuff I've just shown you. They will at A level, but they won't at GCSE. At GCSE, they will ask you what the role of each of these registers is. And that's what you need to be able to answer. So what is the role of the program counter? It's to store the address of the next instruction. What's the role of the current instruction register? It's to store the instruction that's currently being executed. What's the role of the memory address register? It's to store the address that we want to get from RAM. What's the role of the memory data register? It gets the data that is contained in the address that's currently in the memory address register. And finally, what's the accumulator? That's the running total for any mathematical operations that the processor is doing. As long as you're able to define the role of each of these, that's fine. You've got more chance of remembering the roles if you understand the process. That's why I go through the process, but you don't need to explicitly remember that step-by-step process. Okay? The only other parts of this, other than those registers, and we're all really good at this, so I don't think there's too much of a worry, is the arithmetic logic unit, which does all the addition and the ands and the ors and that sort of stuff, and the control unit, which is the one that is doing the stuff we just looked at, the fetching and executing stuff. Okay? So yeah, so that's that. Are there any questions? I went through quite quickly, but any questions on the stuff I've just said? Any specific questions that I said I didn't understand that you want to ask now, and I can go through it? If not, if there's something else you want me to go through, another topic in there, I can do. So, as well as all the garbage you're putting into chat, if you could let me know if there's something you want me to look at, if you want clarification on something I've just said, or if there's another topic in hardware you want me to revisit. Okay, I don't know how much of it was, apparently I cut out a little bit there. So all I'm saying is, if the stuff I've just been talking about, and I've talked about it quite quickly, so I get that I might have missed a bit. If there's something you want me to, not sure about, if you've got a specific question, ask it in the chat and I'll answer it. If not, what's the next bit you'd like me to revisit in this unit before we do the tests next week? Guys, can we stay on topic, please? Thanks, Rachel. What were the accumulator arithmetic logic unit length? That's a really good question, actually, Michael. Right, so they're both used. Say we're doing some addition. We can also do ands, ors, nots, etc. We cover that in the next unit, so I'm not going into too much detail about that right now. But let's say we are adding stuff together. So we've got 2 numbers. What it can't do is just take 2 numbers and work with them simultaneously. It can only have one working value. So what happens is the first number goes into the accumulator. So let's say I'm adding 5 and 3. 5 gets put into the accumulator, and then it fetches the next value, so that's the 3, and then it and the accumulator are both connected to the arithmetic logic unit. So the arithmetic logic unit is able to get the value from the accumulator and the value we passed it, and perform the addition, and then the answer goes into the accumulator. So if the arithmetic logic unit is adding stuff together, it will be constantly getting the current value from the accumulator, adding to it, and putting it back in the accumulator. It's where it keeps its running total. That's what it's for. The 2 are connected directly because everything the arithmetic logic unit does, the answer always goes to the accumulator. And usually the thing it's adding comes from the accumulator as well. Right. We are going to have to do a register as well because I need to keep track of who's actually in here. So you give me 2 seconds while you're in this. So if we've got any more questions, great. If not, which of the other topics you want to go through? If at this point you're thinking, I actually bring this test on, I'm totally confident I'm ready, then that's fantastic. I'm really pleased with that one. So we can use the remainder of this lesson. So we've got, what, about 20 minutes or so, 25 minutes or so, not sure. We've got that that much left to do your own revision, to make your own notes and to go through it. I'll still be around here, so I can, if you post something in the chat, I'll reappear and I'll answer questions on it. But what I do need to do is do a register of who's shown up, so I can send passive-aggressive